direct, I suppose. My name is Dariusz. I am a pleasure to be a representative of the research team from the University of Science and Technology in Bydgoszcz, from Poland. In my presentation, I would like to present you our first attempt to determination of the crack resistance of the layered material built on the base of the two alloy from aluminium and titanium, built with the use of the high energy method. It's called explosive welding. After a short introduction, we will present the research object, some aspects connected with the experimental setup, few results of our test, and short sample. The material which is a topic of our presentation, the main range of application of this material is aerospace, mainly outer space, and aviation and industry. Such materials must meet a lot of requirements. The basic first of them is low weight, of course, but also the radiation hardness, ballistic resistance, and of course resistance for crack propagation. If you want to use for such purpose homogeneous material, it's not too easy fulfill such requirements. One of the idea how to meet this requirement is the use of the layered material like this, built from the more than two quite different materials. The next problem is how to join such materials, how to build such layered material, especially if you want to use metallic material. One of the methods is the explosive welding. This method was developed in 1960s. It was introduced as in the industry. This method is using the explosive material, which covering the clad material. After the explosion, this explosion is producing a kinetic wave, which builds a specific bonding zone of the material. This bonding zone is very good explained in a lot of application. So I will show you only the results of our test without the explanation of the microstructure of such material. We can join with the use of such material, of such method, a lot of different materials. Our material was developed with the cooperation of the few research institutions from Poland, with the cooperation with the company called Explomet, which is a very experienced company in Europe. This firm is delivering a lot of different layered material built with this technology. Our material is a composition of two alloys. The first one is titanium alloy, here's the description, and aluminium alloy. The materials are mainly used for innovation industry, for covering of for example, airplanes. And additionally, the interlayer was used. It was aluminium alloy Al1050. This material was used for improving the process of explosive welding. Of course, such technology requires a lot of heat treatment before the joining, after the joining, but it was described in the other publication. The chemical composition of the base material was shown in the slide. This is the aluminium alloy, here is the titanium alloy, and here is the view of the complex bonded zone. This is a typical shape of the wave where we have a different processes of joining of the material. For the test, we have used 3 types of the specimen. First one is standard tensile specimen. This type of specimen was used for the tensile test with the use of typical hydraulic grips. The second type was the pin-loaded tensile specimen. Such specimens were used when we have made tests with the use of special cryogenic chamber, and the last one was the typical compact tension specimen. A specific feature of all of the specimens is the thickness, because we have used the different material, but we want to compare the results taking into account the final thickness of the material. The plates, all the plates, have the thickness above 10 millimeters. The dimension of that specimen is according to ASTM, and the ratio B to W was 4. Some words about our experimental setup. We have used a typical fatigue testing machine, but not typical was the chamber, which gives us the possibility to use liquid nitrogen. All things, specimen, grips, and other equipment element was immersed in the liquid nitrogen, which gives us the required temperature condition. And here is a process of filling the chamber by the nitrogen. The tests were, of course, realized in both conditions. For ambient, it means about 20 Celsius degree, and in cryogenic condition, it means about 197 minus degree Celsius degree. Of course, during the test, we have measured the COP in both conditions. Additionally, in ambient condition, we have the possibility to measure the crack length with the use of special equipment. It was mainly used for, in this type of test, it was mainly used for preparation of prefracs in specimen. Why it is important? Because we have 2 different materials in our layer material, and the crack propagation in aluminum and titanium alloy is different, and it was necessary to measure the crack length on both sides, and how it was done using the system which is called Effective View, with a special software which uses a digital image correlation method. During the test, one moment, it should be short movie. Okay. During the test, the displacements of the points around the crack were calculated, and on the basis of gradient analysis, the actual position of crack end was determined. So, this procedure was involved in the computer code for system control, and after achieving the required length of the crack from one or second side of the specimen, the system was stopped, and we have obtained the specimen with a very similar length of the crack, initial crack. But of course, the problem still exists that we have a different length of the specimen crack in the titanium and aluminum. After the tests, we have compared the crack line in few specimens. For example, here we have the crack line in the aluminum alloy. the crack length is bigger than in titanium. Here's almost the same, and here's quite another situation. Analysis of the surface, pre-crack surface of titanium, aluminum, and layered material shows that the problem of the preparation of proper crack line in the compact tension specimen is very, very hard and difficult, and the only answer is to produce a lot of specimen and check only the good specimen after the test. Yes, and what is the reason? Of course, we have used the fatigue process for initiation for realization of the cracking process. It means that we have few different problems. The first one is the crack initiation phase different for aluminum alloy, different for titanium alloy. The crack growth rate for aluminum and titanium is also different. So it means that if we want to obtain similar crack length in the aluminum and titanium, we should make for sometimes few or more than few tests. Okay, some results. At the beginning, I would like to compare the tensile test made for titanium, aluminum, and our layered material. The biggest differences was for the titanium alloy. For ambient condition, the ultimate stress was about 900 megapascals, but in cryogenic condition it was 1,400 megapascals. It means we have quite different material here. For aluminum alloy, also the ultimate stress was growth, and then in comparison to ambient temperature, and similar effect is for specimen made from aluminum, titanium, layered material. If we want to compare the microstructure of the cracks after the test, we can observe that in cryogenic condition we have more brittle situation, and of course we can also observe the delamination effect, this bonding of the material as a result of the stresses which exist inside the material. If we compare the result of the standard fracture test, the result is okay in opposite. Yes, in cryogenic condition, the fracture toughness is lower than in ambient temperature, and for titanium, especially for aluminum, the ultimate stress is very similar, but the slope here is different, and it means if we want to use the equation from the standard for cryogenic condition, the KQ value will be a little bit bigger than for ambient temperature. If we want to compare different materials, here is aluminum alloy, titanium alloy, here's aluminum alloy, and our layered material. It is very big differences between material, and the layered material is between the values. And for cryogenic condition, of course, the parameters of describing the fracture toughness are lower than for ambient temperature. And here is the comparison of our material, our layered material. Here is the comparison of the result of the test. Here is the net stress, not the force, because the cross section of all of the specimen was not the same value, and it gives us the better condition for comparison of the results. So I have no time more. I only show you quantitative analysis for our light material in ambient temperature is about 42. This is a KQ parameter, and for lower temperature it was 47. Sorry, this is for cryogenic condition and for ambient temperature. And some conclusions can be read from the slide, and I know it's finished. Thank you for your attention.